People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
Hello, Breaking Math listeners. This is your host, Gabriel Hesch. I am thrilled to announce that today I'll be doing an interview with the author of a popular mathematics book called What's the Use?, with the subtitle How Mathematics Shapes Everyday Life. Now, the book is authored by Ian Stewart, and some of you may be wondering, who is Ian Stewart? Prior to this interview, I went ahead and pulled up the Amazon page for Ian Stewart, and there's quite a lot to say. Dr. Stewart, can you tell us a little bit about your background?
Well, I'm a retired math professor. I was and still have some activities at the University of Warwick in England, which is a particularly well known in the mathematics community because it's one of the best math departments in the UK. But I retired about 12 years ago, and I do a lot of popular math writing. I also write science fiction as a sort of sideline. And I'm still doing math research. I have a very good friend in the States. He lives in Columbus, Ohio, and we've been working together for about 40 years now. Math actually at research level is a social activity, but it's a very small social group. And
yeah, I think you're absolutely right. What's exciting about this podcast in particular is I think it's found people who are passionate about mathematics the world over, and That way, like it narrows down your audience, so you don't have to cater your audience as much. So wow, yeah, that's very cool. You had mentioned you've authored some science fiction. I've now interviewed 4 different either mathematicians or physicists who have gotten into science fiction. What got you into science fiction?
I got interested in science fiction when I was about 13, which is a fairly standard sort of entry route. And I just enjoyed the books. And I now have a collection of 8,500 books and magazines in the house, which
wow.
my wife kindly tolerates.
Wow.
Yeah.
I have to ask you this question real quick. So when I ask myself that question about my own interest in mathematics and science fiction, I think about elements of stories themselves and, fantasy, and then what separates fantasy from science fiction. There's a book called Harry Potter and the Methods of Rationality. Have you heard of that one yet?
I've heard of it. I've not read it. But a few years ago now, have you heard of Terry Pratchett?
Yes.
Okay, because I've done 4 books with Terry Pratchett and with a biologist friend of mine who died a few years ago. We did a series of books called The Science of Discworld. And of course, what people always assume that's about is it's like these sort of Science of the X-Files and so on books, Science of Star Trek, which uses the TV program or the movie or the book as a vehicle for explaining, how does the warp drive in Star Trek work? That kind of thing. Well, we didn't do it that way because when we had the idea, we talked to Terry Pratchett and said, Terry, why don't we do a Science of Discworld book, a bit like these Physics of Star Trek and so forth? And he said, I'd love to do that, but there's no science in Discworld, it's fantasy. It's based on the power of story, it's based on narrative imperative, and it's based on magic. And magic is what happens when people want, and science isn't like that. But we found a way to do it, which is that in the fantasy world, so basically Terry wrote a short story. For readers who don't know about this world, it's a fantasy world with witches and wizards. It's flat. It rides on the back of 4 elephants on the back of a giant turtle who swims through space. And he used it as a vehicle for satire, basically. But we found we could use it to talk about science, provided that the wizards of Unseen University on Discworld brought into existence by magical means Roundworld, which is our universe and our planet. And from the outside, they observe what's going on in Roundworld, and it makes absolutely no sense to them because it's not even a flat world like any sensible world ought to be. Mm-hmm. So we then intersperse chapters commenting on what is puzzling the wizards. So everything that we write about is actually going on in Roundworld. It's in our universe. But the story kind of sets it into the Discworld setting. And this turned out to be a very enjoyable and fruitful way of talking about any bit of science we want.
Yes.
It doesn't have to be something that has any connection with Discworld as such. It just has to be something that the wizards are observing going on and thinking, what on earth are these people doing? So we had a series of four books. We were only going to do one, but it was all the fans liked it, so they insisted we did a second one, and it kind of carried on from there.
Oh, fantastic! So for our listeners right now who want to read that book or any of your other previous books, where would you suggest?
There is some math in that.
Oh, yeah.
Which of my books should people start with? One that has been very successful and that I really like and really enjoyed doing. Don't let the title put you off. It's called 17 Equations That Changed the World, or in the American title is less off-putting because it doesn't mention equations.
I know, those are so scary, aren't they, for everybody?
In Pursuit of the Unknown is the American title.
Oh, okay. That's
so the unknown is what the equations are about, of course.
Yeah.
But it takes about 18 or 20 really important mathematical equations, explains their history, explains where they came from, and what in our lives now depends upon mathematicians and physicists and engineers and other such people having come up with these equations and understood them. So, for example, radio and television depends on the wave equation for electromagnetic waves, and so on. So, In Pursuit of the Unknown, that's a good one to start with, and it tackles equations head on.
Nice.
But you don't have to actually understand the equation.
Yes. You know what? I saw a really good show on Stephen Hawking's information paradox with black holes, and it was actually produced in Britain. Oh, gosh, what was it called? It may have just been called the information paradox. It was released probably 18 years ago. But what was really cool is it took that approach. It actually took Stephen Hawking's approach on information entropy and black holes, and it took every single letter, every single one, and it had a neat diagram and picture and story. Now, not heavy math at all, just like stories and things that people can relate to.
Yeah, this started out. It was actually a Dutch publisher who asked my English publisher whether they had anything of this kind, and basically the response was no, but we can get one written.
Oh, nice.
And it was, but the idea, yes, I think in show business there's a saying which says, if you have a wooden leg, wave it.
Okay. Nice.
Yeah. If there's something that you really would quite like to conceal, don't.
No. Okay. Yeah.
Put it right up front. So every chapter starts with a page which has the equation in very big letters, with lots of arrows and things saying what the symbols are and what they mean. E equals mc squared, E is the energy, m is the mass. I don't actually use that equation because everyone knows that one.
Yeah.
Maybe the only one they don't. And it tries to make the equation seem friendly because equations are telling you something. They contain a lot of information. This is why mathematicians like them. They're a very compact way of representing key ideas in mathematics.
Yes.
So if you can start to treat equations as something that isn't off-putting, but is kind of not exactly warm and fuzzy, but at least friendly. It's trying to help you.
Yes. No, I hear you. Early in our Breaking Math podcast ideas, or our idea phase, we did a lot of promotion on social media, and one of the things that we wanted to make equations relatable is we actually took a whole series of famous photographs and famous paintings through all history, tons and tons of them, and we would superimpose a mathematical equation on the top or the bottom to get people to think. Now, the first one, you're going to laugh. You know that famous photograph of Marilyn Monroe where her dress is blowing up over the vent?
Yes.
We did that one, and beneath that, we put the fluid dynamics equation.
I was thinking you might.
Yeah,
yes.
Exactly.
Aerodynamics.
Yeah. We did.
Absolutely.
And there was a couple other great ones, and these are nothing more than conversation pieces. Like, okay, what does that equation have to do with what's happening here? There's another one we did where there's a famous photograph that I recently heard was actually fraudulent. In other words, it didn't actually happen. It shows a bunch of construction workers eating their lunch on a beam. Do you know what I'm talking about?
I know the one. Yeah, I think I know the one you're talking about.
Okay, it's possible it was fake. I mean, whatever. You
can fake almost anything. Yeah.
Oh yeah. So that one we did potential gravitational energy because that's pretty obvious. There's one that I never did that I've been wanting to do. I want to superimpose an equation. I just haven't found the right one on what's the painting? Is it called The Scream? Where it shows a person just slapping their face and screaming.
Yes.
So what would be the most horrible equation ever that drives physicists, to madness that we could put on there? Maybe turbulence or something?
No, I mean, the obvious one would be the wave equation for sound.
Okay, yeah.
Yeah, but I mean, it's what's going on inside his head that's really the point here. It's what's driving the scream, isn't it? So you want some sort of... there's a thing called the Hodgkin-Huxley equation for the nerve impulse, which is one of the things mathematical biologists use to understand how the nervous system works, and in particular the brain.
Yeah.
So at least you'd be getting towards sort of brain mathematics rather than sound.
Okay.
But it's the interpreter, it's the mind, it's what it means to the person who is screaming.
Yeah.
And that's much harder to turn into an equation, I think.
Yeah, totally. So, yeah, that'd be fun. Now, I would like to real quickly redirect toward the book that you are selling right now. The book is called What's the Use, and it's available right now on Amazon or anywhere folks buy books. I saw it at Barnes & Noble on their website and all kinds of places. So What's the Use, of course, the inspiration of this is kind of what we're doing right now. It's explaining what's the significance of a given math and how do you use it every day. That's essentially what you'd say the purpose of the book is?
Yeah, it's a kind of, what is math doing for us? Why do we have mathematicians at all?
Yes. Okay.
From the point of view of somebody who's not in the academic world, who is not necessarily into anything scientific. They're just living their lives the way we do nowadays. And one of the points that the book starts with making is you don't see the math
Yes.
that is being used. You
Yes.
pick up your phone. A phone is an amazingly complex mathematical machine.
Yes.
Smartphone, a cell phone. The amount of math that goes into a cell phone without which it would not work
Yeah.
is enormous. And the user does not see this, probably doesn't know this. Why should they? You don't need to. I mean, when I use a phone, I don't actually think very hard about the math. If you had to, then nobody would ever buy one. But without the math, those things won't work. So we need to have enough people, and it turns out to be rather a lot by the time you put all this stuff together. Yeah, so one of the ideas was to try and explain to people that you may not see it in action, but it is happening all the time in stuff that you're using.
Mm-hmm.
And the other aspect of it was to try and make the math interesting in its own right and surprising.
Yes.
With perhaps the biggest surprise of all being that that kind of math is getting used for this kind of problem. Because nearly all of the math that's in the book was not invented with the current use in mind. Yes. Some of it wasn't invented with any use in mind. And it turned out a few hundred years later, gosh, well, we can actually make use of this stuff.
Yeah, isn't that wild?
And then it turned out to be really quite important. So I was trying to collect stories which are a little bit surprising because I tried to put over the message that you can't judge a piece of math purely by its content. Math that seemed to be about something that's totally unrelated to the real world can overnight turn into something that is very closely related to the real world because it suddenly turns out to be useful in solving some kind of real world problem.
Yeah, that's one of my favorite parts of mathematics. In fact, one of our first episodes we actually talk about useless or quote unquote useless math that eventually had a purpose, and the greater, I guess, philosophical musing of how does human knowledge work. It's almost like mathematics, pure math. And then, like, what's the opposite of mathematics? I guess just like intuition. I don't know. We're talking about like two strands of DNA about how we understand our world. You know what I mean? And yeah, pure mathematics is definitely part of it. And you don't know what you don't know. So I'm trying to make this sound deep here, but I think I'm stumbling.
Right. Well, no, but there is a philosophical point here, and it's one that I don't think anyone still understands. There was a physicist called Eugene Wigner, who gave a lecture about the unreasonable effectiveness of mathematics.
Yes.
And the important word there is unreasonable.
Yes.
If mathematicians study, and physicists and so on, study the flow of air around objects, and you end up with aerodynamics and it helps you design aeroplanes that fly, that's not a surprise.
Yes.
It's very worthy, it's very important, but it's a reasonable use of mathematics. It was invented for that purpose.
Yes.
But if you take something that somebody came up with off the top of their head just because it looked like fun about 300 years ago, and suddenly it turns out to have medical applications or technological applications to something that they could never have, the inventor of this math could never have imagined was possible, then that's an unreasonable use.
Yes.
So the book is about the unreasonable uses.
Oh, yeah.
Because they're more fun and they're more surprising.
Yes. Oh, yeah, for sure. One other thing we talked about prior to this interview, while we were just getting set up, is who the target audience of this is. And I found that perhaps I have a bias. I was going to say, even like a high school student who's interested in mathematics or, I don't know, even down to 8th grade. But then I thought, no, wait a minute. I say this as somebody who already has a master's degree in electrical engineering, so I've already been familiarized with a lot of this stuff. So it's kind of hard to tell exactly who it's for. However, you and I both said if there's an unfamiliar term or an unfamiliar concept, it's so easy this day and age to go to YouTube, or even Wikipedia is fairly reliable, a lot of the time. So
it's pretty good on math, actually.
Yeah. So really, I would say anybody who is passionate about math, you won't be solving any equations in this. I mean, you could, but like you won't be doing a lot of math yourself, so you can read the book and
it's not trying to teach people things.
Correct.
It's just to inform people who are interested. You need to have some sort of sympathy towards the idea of reading something about math, I think, is as far as it goes.
Yes.
You don't have to be an enthusiast, you don't have to be a fan. I try to explain the technical ideas in non-technical terms. There are lots of pictures, which I always find helpful to illustrate
Yes.
ideas. The idea, the point of it is to try and make it as accessible to as many people as possible. I never have a specific target audience in mind for books, because I think books tend to find their own audience, in fact.
Yes.
I once had a long argument with a television producer about this, who reckoned that if you're doing TV, you know exactly who your audience is going to be. And I said, well, it's really not like that with books. Publishers get big surprises.
Yes. Yeah.
They think they're onto a winner and it flops. They do a book they think no one's ever going to buy and it ends up on the bestseller list.
Isn't that amazing?
And isn't it nice that it's like that?
Yes.
If everything was predictable, it would be so boring. And
that itself, I think, would be a fascinating story, a fascinating podcast. It's just to sit with some of these seasoned book publishers and talk about their surprises and their misses and all that kind of stuff, So.
No, it's one of the things I quite enjoy about writing the book, because to some extent I write it because I'm interested in it, and I think other people will be interested if I can tell them about it in a sufficiently accessible way.
Yes.
And then we get to see whether, in fact, that's true.
Yeah.
And what happens. Had a big success some years ago with a book which was just a collection of about 200 very short pieces of miscellaneous interesting math. It was called Professor Stewart's Cabinet of Mathematical Curiosities.
Nice.
Yeah, it went to number 6 on Amazon in the UK.
Fabulous.
Just after Christmas some years ago.
Wow.
And nobody expected that, including me, my agent, and the publisher. It was the right book at the right time. I think people were looking for Christmas presents and so on. If it's only 2 paragraphs long, then you're not going to get bogged down in anything that you can't bail out of and move to a different page.
Yeah, for sure. Entire list here of books. There's a lot I'd love to read here, and I'd love to talk about. Like, I don't know, you had mentioned earlier in the interview a few recommended spots to start with. But yeah, if you've got any other suggestions among your publications, let me know, because I'd like to fill up my basket while we're talking.
Okay, if for people, one of the things that's very interesting about math for people who are that way inclined is the history.
Yes,
because it has a very, very long history.
Yes.
It goes back at least 4,000 years to the ancient Babylonians, and some of the things that the Babylonians understood are still in use and worth knowing today.
Yes.
They were pretty smart mathematicians, in fact. So there's one book I did called Significant Figures, which is essentially it takes 25 important mathematicians, not the most important, for all sorts of reasons, but 25 who did something of considerable significance mathematically. It might or might not have applications. And roughly speaking, I try to arrange them in approximately historical order so that there's a kind of mathematical thread that runs through the whole thing.
Okay.
So I think people who are interested in the history, it perhaps differs slightly from some of the other history of math books, because it's really driven by the people and their story. The math is just part of what they do.
Wow, very cool. And you said this, and I didn't catch it. The name of that book? Significant Figures.
Significant Figures.
I did catch it. Okay, I thought for a minute that I didn't catch it.
You did.
Okay. What's interesting is, as I'm talking to other folks who are academic in nature and who have, say, a podcast or a TikTok or whatever about an academic topic, a lot of the folks who make things on, say, history or philosophy, they say, "Oh, mathematics, that's terrifying." So if there's a book that's more focused on the history of mathematics, that might give them something to chew on and to relate to. So that's really cool, actually. Now, as we're talking, I have this whole list here on Amazon of your other publications, and there's some interesting ones here. There's a book titled Fearful Symmetry. What is that about?
That's about pattern formation. It's about the math that helps us understand a lot of striking patterns in the natural world.
Okay.
So if you throw a stone into a pond, you see circular ripples which spread out from the center.
Yes.
Well, that's a mathematical pattern, the circle. It's a very simple object, but it's also a very symmetric object.
Yes.
Mathematicians are very keen on symmetries because there's some beautiful mathematical theory behind it called group theory, which kind of formalizes the idea of a symmetry transformation. A symmetry isn't a thing, it's a transformation. The symmetries of circles are, if you rotate a circle through some angle, it still looks like a circle. If you've got a square, you have to rotate it through 90 degrees. Otherwise, you'll notice that it's moved. But if you have just a blank square and turn your back and someone rotates it through 90 degrees and you turn around and have another look, it will look exactly the same. Actually, It's moved. So the symmetries are the ways to move objects, which leave them looking just like they did beforehand. And there's a whole beautiful mathematics of pattern formation, which covers a huge number of different types of application from biology through to engineering, using essentially the same basic mathematical toolkit, which is a mixture of this group theory, which is the kind of algebra of symmetries, and dynamics, which is the mathematics of how things change with time. So, So fearful symmetry, it's you probably recognise there's a William Blake poem, Tiger, Tiger, burning bright in the forest of the night, what immortal hand or eye dare frame thy fearful symmetry? So grubbing around for a title, he ended up with fearful symmetry as the title.
Oh, okay. Very cool. Very cool. I like that. Interesting. Yeah, we...
So in fact, stripes on a tiger are an example of this kind of pattern formation.
Yes. Yeah.
There's a mathematical equation which governs how the stripes form in the embryo before the tiger's born.
Oh, wow. Crazy.
So there's a pattern which is not visible when the tiger is first born, but there's a chemical pattern on the skin which at a future stage triggers the formation of the proteins in the hair which give it colour.
Yes.
And that's where the stripes come from. So there's a pre-pattern which is laid down in the embryo following mathematical rules, which then, as the tiger develops, some bits go black, some bits go brown, some bits go white, and you get a stripy pattern.
Mm-hmm.
I like tigers.
Nice. That's cool. So now, when you talk about symmetry, I was curious if this topic was brought up in the book Fearful Symmetry, and that is in physics and in the history of the universe, breaking symmetry.
Absolutely. In fact, breaking symmetry is the pattern forming mechanism. So the idea is that, in fact, there's two different ways to break symmetry. One is the mathematical equations remain symmetric, but the solutions stop being symmetric.
Okay.
That's called spontaneous symmetry breaking.
Yes.
And then there's another one, which is you actually change the equations so that they're not quite symmetric anymore. So you kind of give them a bit of a nudge. Yeah. So that mostly what the book is about is the spontaneous symmetry breaking, which in physics, for example, the Higgs boson, which was this very famous particle discovered fairly recently, yes, which gives all the other particles mass.
Yes.
Now, the Higgs boson is an example of spontaneous symmetry breaking. It doesn't, the mathematical equation for it has circular symmetry, but the state of the particle is not circularly symmetric.
Yes.
But I can give an example that's perhaps a little, one that I'm fascinated by is the patterns of sand dunes. If you look at Google Earth from high above at a desert, you will see amazing patterns in the sand dunes in the Namib Desert or indeed on Mars. You have to go to NASA's website for that, but there are enormous fields of sand dunes on Mars. And they have patterns. They have quite interesting, often quite regular patterns. In fact, the simplest one is like the tiger. It's stripes, long parallel dunes. Now, those form the kind of equation that governs the formation of these dunes. The desert starts out completely flat. It's like a blank sheet of paper. It's very, very symmetric, boringly symmetric, because if you can move a sheet of paper any way you like and it still looks like, if you just focus on what's in front of you, it looks like a bit of a sheet of paper. You can't really tell if it's blank. As soon as you rule some straight lines on it, then those move around. But if you have parallel lines and you move them at right angles so that they just move one line across and then they overlap again, they end up looking exactly the same. So stripes are a series of equally spaced parallel lines. That's a symmetry, and that's a broken symmetry from the flat desert. And all of the sand dune patterns can be explained and understood in terms of breaking symmetry from a flat desert. There is also the possibility that the wind is blowing, and if the wind is blowing in irregular ways, which it can do, now you're breaking the symmetry of the equations as well. So you've got the other kind of symmetry breaking. But it would be possible to write an entire book about the mathematics of sand dunes.
Wow, that's fast. Yeah, that's a topic where I hear what you're saying, but I'm trying to comprehend symmetry breaking, and there's a feeling when I really understand something, and I definitely am not there yet. Obviously, I have, I'm grasping it like, well, why, and like, you know what I mean. So that's that's quite a topic. So,
Okay, yeah. Yeah, I mean, there are some simpler examples than sand
Yeah.
dunes, but those are very visual.
yeah, very
The,
cool.
the mathematics is just that if you have a symmetric system of equations, then there is always there's a solution of the equations which has as many symmetries as the equations do. It has all of the symmetries of the equations. But physically, that can become unstable. That is, you won't see that solution happening. It's like a pencil balanced on its point. In theory, there is a perfect balance point, which is completely symmetric under rotations if it's a round pencil. But you can't balance it there. If you let go, it will fall over.
Yes.
It's broken the symmetry.
Okay.
But in fact, there's a whole circle's worth of directions in which it could have fallen over, just depending which way the tiny breath of wind was blowing.
Yeah.
So a pencil balanced on its tip and what happens when you let go is actually a very good mathematical example.
Okay. Very cool. Very cool.
But
Awesome.
not a very exciting one.
Well, so sort of. Now, again, I'm a little obsessed with math because I don't know. I think it was a show I was watching from Neil deGrasse Tyson on The Big Bang, and again, it's pressing that question of, well, how do you know this? You say all these things, but how do you know? And it's for that reason that even if something might even seem uninteresting, I'm still obsessed with it, and I still file it away. Like, okay, so this will explain something down the road or something. You know what I mean? So it's even if something is not really super intuitive or clear, I don't know. It's certainly worthy of discussion. So. That's for sure. One of the things that I want to mention, and again, you'll have to forgive me for my jumping around style. I just think of so many things that I just have to do this. So in your current book, there's one chapter that I read several times, and I realized there's a reason why I read it so many times. The chapter was called Papa, Can You Multiply Triplets? The reason why I read it so many times was because there was a rather recent video from the brilliant YouTube channel 3 Blue 1 Brown, where he illustrates graphically exactly what quaternions are. He does many examples, and you see beautiful graphs in 3D, and those two tied together so well. So for all of our listeners, I want to suggest that they read that book, but also watch that YouTube clip on quaternions. It'll help. Now, I'm sorry, I feel like I interrupted you. You're going to tell us a little bit about that chapter?
Yeah, that's a fascinating story because it's about William Rowan Hamilton, who was an Irish mathematician.
Yes.
Back in the 1800s, who was essentially trying to invent a new number system. And it was a number system that would let you do three-dimensional geometry. And the precursor of this is something that for mathematicians is perhaps one of the biggest discoveries, most important ever, is what are called complex numbers.
Yes.
This is where you allow -1 to have a square root. But the natural geometry of complex numbers is the two-dimensional plane. And enormous amounts of physics in 2 dimensions can be done using complex numbers. So Hamilton wanted to do the same for 3D. And he spent years trying to invent this new number system. And eventually he figured out you couldn't do it in 3D. In fact, nowadays we can prove you can't do it in 3D. But you can do it in 4 dimensions. And this is why they're called quaternions. The quater is the Latin for 4. There's basically 4 different basic numbers which you combine together by adding them to get all of this system of quaternions. So inside the 4-dimensional space is a 3-dimensional space where you can use them to do various things in physics. So Hamilton invented these, and he was quite obsessed with them. And I think a lot of people at the time thought he was a bit of a crackpot about it. He was a very good mathematician, but he kind of got bee in his bonnet about these strange quaternion things. But they did turn out to be very useful, not for the kind of physics he had in mind, but in mathematics itself, in the computer graphics industry for games and movies, because what you want to do in those is move objects around in 3 dimensions and project them onto your 2-dimensional computer screen or movie screen.
Yes.
And you want them to look realistic.
Yes.
And so you need very efficient, fast ways of representing motion in 3D, moving sideways, rotating, spinning, all of this kind of thing. Hamilton's quaternions are absolutely perfect for that. Essentially, they eliminate errors that might accumulate if you tried other methods. Mm-hmm. And the other thing is they're now turning out to be actually quite important in fundamental physics, particle physics, mm-hmm. areas like that, which were not the sort of classical physics that Hamilton had in mind.
Yeah, in fact, you know, I have a colleague that we start after Breaking Math. We began a YouTube show called Turing Rabbit Holes, named after Alan Turing. My co-host was Dr. Alex Alanis. He was obsessed with quaternions and their use in particle physics. We never really did a show on it, but I'm curious, what can you tell us about their use in particle physics?
Okay, I mean, basically, the key to particle physics is symmetry, but fundamental particles are very, very weird things, even to physicists. Now, there's some sort of bunch of waves in a quantum world, and they obey quantum rules. But there are symmetries in particle physics, which are not just the physical ones. If you can take a particle and move it, or you can rotate it, you can actually transform it into a different particle.
Mm-hmm. Oh, wow.
You can apply a mathematical transformation to the equations, which solutions that would be one kind of particle are then turned into a different kind of particle. Mm-hmm. And the symmetries that crop up here are, among other things, these quaternions and objects like them are fundamental to the mathematics of understanding those symmetries. So there's the standard model of particle physics is a rather complicated bunch of equations which have quite a lot of symmetry, but the symmetries are what mathematicians call continuous groups. They are not just you move something, you know, in a small number of different ways. You move them in infinitely many different ways. So in the way that I could take an object, hold it in my hand, and move it sideways any distance I like. So that would be potentially an infinite number of possible distances I could move it. Whereas with a square, if you want symmetries of a square, there are only 8 symmetries. You can rotate it through 4 different angles, and you can flip it over about 4 different axes. And that's it. There's 8. The quaternions are not greatly useful for these finite groups, but for the continuous ones, they often show up. They're very basic to the whole area. So physicists working in those areas have to have some understanding of quaternions. Mm-hmm. And some related mathematical gadgets. I mean, it's a very well-developed, sophisticated area.
Nice.
And some of them really like thinking about quaternions and get... they're fascinating things because they're a bit of a twist on the usual number systems we have. They don't obey all of the rules of algebra. That was the other thing that Hamilton didn't understand at first. He wanted all of the rules of algebra to apply. Mm-hmm. And in particular, the order in which you multiply 2 numbers together shouldn't make any difference to the answer. So 2 times 3 is 6, 3 times 2 is 6. Yes. And he thought that should happen for his number system. You can't do it that way.
Yeah.
Quaternions, when you multiply them in a different order, you get a different result, usually.
Oh, yeah, kind of like, and again, I'm going to expose my ignorance here, sort of like in matrices, how you can multiply. You can.
Yeah, well, you can represent quaternions as 4x4 matrices.
Okay.
Of a particular kind. Cool. And so, it's all of this stuff is related, but with rotations, if you rotate an object through 2 different angles about 2 different axes in space, depending on which order you do those rotations, you can get different results. Wow. So it's not surprising, given the link between quaternions and rotations, it's not surprising that they don't obey this commutative law of algebra, as we call it.
Yes. Yeah.
Because the thing you're trying to model, which is movements in space, that doesn't obey that law.
Mm-hmm. Yeah.
It obeys almost everything else.
Interesting.
Yeah.
Yeah, very cool. What I love about this interview itself, and I'm sure you've experienced this many, many times in your research and in your discussions, are how when topics overlap each other. Because, we were just talking about symmetry, what was it, 10 minutes ago? And then we talk about quaternions and how symmetry is a huge aspect of that with respect to, particle physics and things like that. So that's one part of this that I love, talking about math. It's just, everything overlaps. So that's pretty cool.
Yeah, it's unified. It's something which I think when we first do it in high school or earlier, it comes in. There's arithmetic, there's algebra, there's geometry, trigonometry, and so on. And you don't see many connections between them, at least not to begin with.
Yes.
But really, they're all part of one much bigger picture. The problem is the entire picture is so huge that no living mathematician would actually understand all of it.
Yes, yeah.
There are some who come close, and they're very impressive. But no, most of us find an area within the subject that appeals to us, and we kind of specialize in that. If we've got any sense, we keep an eye on what's going on everywhere else in general terms. Because sometimes it's important for what we're interested in.
Yes, yeah.
And I'm not saying that's the test of whether it's worth doing, but it's the test of whether we should pay attention to it.
Yes.
But it's a huge subject. I mean, my research colleague in the States and I are putting together a book on our part of research mathematics, which is about networks and dynamics on networks. Okay. And we've pretty much finished writing it, and it's 900 pages long.
Ooh, goodness. Wow.
It's going to be a big fat volume, but in order to tell the story and the applications as well as the theory, we eventually decided we just had to make it that big. There's just a big story to tell. So, and that's our tiny little corner of mathematics.
Yes. Dang, that's fascinating. Man, I'll tell you what, when you're ready to publish it, or just let us know. We would love to have you and any of your co-authors back on the show to talk a little bit about that. That sounds like a fascinating project.
The nice thing about it is everyone knows what a network is. It's it's also called a graph by mathematicians, but it's a lot of dots joined by lines. It looks like a spider's web built by a very drunken spider.
Okay, yes.
But huge numbers of things in the natural world have that structure. Airports connected by airlines is an obvious one. Nerve cells in the brain connected by synapses.
Wow.
Genes connected by this one reacts with that one.
Yes.
And so on. So the network math has lots and lots of interesting applications, and you can find out a lot about it and kind of understand what's going on without getting tangled up too much in the theory. So it could be quite a nice topic.
I had one more question that I wanted to ask you.
Surely.
This probably motivated a little bit selfishly. One of our obsessions on breaking mathematics, or on breaking math, is the topic of mathematical modeling and trying to describe human language. We always try to go about it from Shannon's information theory, as well as themes from the book Gödel, Escher, Bach. So I'm curious, is this an area that you have read much about, or do you have any thoughts on that field?
I've read it. Gödel, Escher, Bach is one of my favorite books.
Nice. Yes.
Of all time. I think it's absolutely brilliant.
Yes.
I have read Shannon and Weaver's book on information theory.
Yes.
One of the equations in my In Pursuit of the Unknown book is in fact the information equation from Shannon. But I'm not an expert on any of that.
Yes.
I'm aware of it.
That's how I feel.
But I think language is very interesting mathematically, but there's a big gulf between language as actually spoken by people and sort of theoretical grammatical structures and some of the things that people were trying to study. But of course, where math and language do come into contact now is machine intelligence. And,
yes.
It is now possible to talk to your computer and it will understand you. I mean, it will talk back to you. And these things are getting surprisingly good compared to what anyone thought was possible even a few years ago. And behind this is a lot of a lot of math, but it's not so much information theory math. It's matrices and graph theory and stuff like that, I believe.
Mm-hmm.
Deep learning algorithms, that sort of stuff.
Yeah.
This is clearly going to be, well, it's already very important. It's going to be more important. It's another one. It's not in the book because, well, I had to save some in case there was a sequel. You can't put all your best material into volume 1 just in case.
Oh yeah, I hear you.
I think all authors, at the back of their mind, you're thinking, well, if you put all the good stuff into the first book, then you don't have many material left for the next one.
No, I hear you. Yeah. Fascinating. Yeah, that's been, it's a topic where, here's how I'll describe it. That's, my intuition is strongly pushing me in that direction for, like, where there's a lot of great, there's a lot of great ideas and things that have not been published yet. It's rich ground for publication. Yeah. I just don't have my I'm not there yet. It's still cooking. If you
one of the things that interests me, and I think Gödel Escher-Bach goes into this to some extent, there's a big difference between information and meaning.
Yes.
Between syntax and semantics.
Yes.
And, the statement 2 + 2 = 5 contains the same amount of information as 2 + 2 = 4.
Yes.
Right, but one of them's correct and the other one's not.
Yeah.
And that's important as well.
Absolutely. And and like, part of what I've thought about is language and how it's used for, or how, I'm not even speaking correct grammar here. I should do an entire podcast of incorrect grammar that is perfectly coherent, and talk about how you can have meaning without necessarily having grammar, and how those rules work. But I've thought a lot about song lyrics that are complete nonsense, yet evoke a strong sentiment, like things by the Beatles or by the Red Hot Chili Peppers. I'll have to think of examples here, but or even things that people can say that sound super deep and are hypnotic, but are complete nonsense. You know what I mean? Like
there's a lot of things. If you look too closely at a lot of lyrics of pop, I when I was an undergraduate, I was lead guitarist in a rock band for 2 years.
Yeah.
We were singing this stuff, and then you think about it after. What did that mean?
Exactly. Yeah.
But but it evoked a response in the audience, and well, we mostly played for dances, and it was the response was they danced to it. But, they liked it.
Yes.
And some things worked and some things didn't. And we rapidly found out which ones didn't. We stopped playing those.
Indeed. So it's almost like talking about, there's physics for poets. We also need poetry for physicists. So I think, Thank you, sir, so much for coming on the show. Come on again. We'd love to hear your thoughts on anything, any of your future publications, or if you wanted to just come and talk about whatever. We'd love to have you. So thanks again.
Thank you, Gabriel. That was great fun. And I'll take you up on that offer.
Wonderful.